Okay, hi. Hello, everyone. I'm very excited to be here with you all. I'm Sejo, pronouns are they, them, and yeah, so I'm looking here at the chat that there's people from many different places in the planet, so I'm very excited to be here with you all. Yeah, so we are gathered here in order to get this introduction to Uxn programming, no? Or Uxn or Uxn in Spanish, or so this is a mystery always, no? How do you pronounce Uxn? Um, so I will be like changing between many possible pronunciations here, I guess. um, I wrote here a couple of like hashtags. I mean, I'm not in Twitter, but maybe in the Fediverse. I know many people that are connected here are in the Fediverse, Mastodon, Pleroma, etc. So maybe you can. I mean, I don't know what to do with it, but I think it could be interesting, not to post live post about the workshop. Yeah, so I'm Sejo, and yeah, so this workshop is brought to you by Babycastles Academy, a very nice, like physical and also virtual nowadays space in New York City, Babycastles. And so this is part of the program of Babycastles Academy, and also Computances, the project that I have where we explore human computing at a human scale, either like what we are gonna be seeing right now, or also like actually dancing or becoming computers with our bodies, no? And well, obviously not obviously, this project Uxn is a project by 100 Rabbits. I think some of them are already in the chat. There's also, yeah, so welcome everybody. Okay, so I see that in the chat, the Babycastles account already shared with you all the link with the notes of that we will be looking at. So those notes, are like this web page. You can also access this site, Gemini protocol, as I'm seeing in the chat. So this page has the description of the workshop, and it has the outline. I will show you the outline in a moment. But everything that I will be opening, or every link that I will be visiting, is already here, no? In these notes. So yeah, I mean, I will be mentioning whenever I'm entering another link, but just in case, everything that will be accessed during this workshop it's already here in this page. Okay, so that related to the website, and also, okay, let's go back to the outline. Well, let's go to the outline. We're gonna be going like through these 7 sections. No? So a little bit the idea here is that in after each of these sections, that will be like about maybe 15 minutes. I mean, approx. I will be able to look better to the chat and actually answer questions. But also, I'm very I feel very good that many people that are already involved in the Uxn project are already in the chat. So maybe also they can help with some questions if you want. No? Otherwise, I can do. I like a lot this process of like going to one section, and then pausing and being able to answer and have questions. Okay, so we will be talking about what is like Uxn in general, Varvara, this virtual computer based on Uxn. We're gonna be introducing the language Tal, and then we're gonna like jump right in after covering like these basics of the computer. We're gonna go right into actually how to use this virtual machine, in order to draw into the screen in many possible ways, introduce some interactivity, and also start introducing some of the logic, like conditional logic, no? That we can use in our programs. Okay, so let's go to the first section. So we will be talking about what is Uxn, Varvara, or Tal, the language, and also we will be talking about the computer architecture of this computer. But before, actually, I want to start this because there's a very let me change here. I'm gonna go to this Uxn site. There's a very nice story behind the project that I will actually not cover a lot right now because you can actually read it and it's very enjoyable. But I want to start sharing this set of images. So these are photos from a project called Unknown Fields. Actually, the website is like, I mean, at least when I checked, it was down, so I had to recover them from the Wayback Machine, as you can see. And these machines, these pictures, sorry, are a reminder. Let me go a little bit further away. A reminder of the physicality or materiality of computing. No? So computing or making computers, these very nice machines that are super fast and super powerful and are upgraded each. I was gonna say each year, but maybe it's like each month. I don't know. No? I'm not up to date with the with that release cycle. But making computers, as maybe I guess, or I hope not many of you already know, but I think it's important to acknowledge. Making computers implies having a lot of toxic waste. Implies also actually handling materials, having a lot of people assembling those devices. Making computers implies destroying places, like rare earth mines, and so on. So it implies destruction, it implies pollution. And also all of these processes that we can see here, the refinement of these materials, the production, or all of these processes also require a lot of energy. So even though you might be creating a new hardware platform that is super energy efficient, if you take in account all the energy that is used in order to actually make it, and not only the energy, but also the pollution, the destruction of places. But it makes you wonder, what to do now, or if I enjoy computing, what can I do now, or what can be an alternative, or not following the mainstream path of bigger and faster computers every period of time, but what can so what if we actually decide, okay, what we have is enough and we can actually use what we have already, like all the electronic computers that we have already, we can use them and have fun with them or create meaningful work for them, either tools or games or whatever. We can actually use them. They are not dead as the mainstream narrative will tell us. So so for me, that's why I'm engaging a lot with this project, Uxn. It has to do with, again, questioning, okay, what if we have already enough electronic devices and we can actually use them already? And also it implies what if we can have fun with computers? That maybe for me personally, after looking at this picture or looking at this big context, it could be a little bit disappointing or depressing. And also the idea of, okay, what if we could scale down to a machine that we can actually understand, and we can actually discuss, as we are going to be doing now in a whiteboard, and we can actually see how it works, and we can have it in our heads. So okay, so that's a little bit about context that I think it's important. The Uxn is this virtual machine that we will be working with. Actually, it's the core of the machine, the processor. It's a virtual processor, but because of Church Turing thesis, so we can. I mean, it could exist as a physical or semiconductor-based processor, but also it can exist in a simulated form, and in a virtual form. So it's a virtual machine, and Varvara is this this system of devices, input devices, output devices, so mouse, controller, console, screen, audio, that uses Uxn at its core. And Uxntal, or Tal for easier pronunciation, is the language that the assembly language that is assembled to the machine code that Uxn can execute. Okay, so I was looking at the chat. Okay, so let's talk a little bit about them. So what is this computer architecture? And again, I'm starting from the assumption that not a lot of people here might know about computer architecture in general, no? Or that maybe some of you already program or have programmed, but in higher level languages, no, where we are more involved about, or more, where we care more about the ideas or the structures moving around, and not a lot about the actual, how is it actually happening in the machine. So we can talk a little bit about that computer architecture. So let's think that, okay. We have a little, I will be making a small block diagram. So let's think that this is this control unit of this machine. So this control unit is able to decode some instructions. There's only, we'll put in 32 instructions. Move this a little bit. That this little machine can perform or execute. Execute is like a kind of a strange word, but yeah. So this machine can perform 32 different instructions. And this little core is connected to 4 different parts. And bear with me for a moment. It may seem a little bit like abstract, but also obviously you feel free to make questions, but also I hope that this is like the anatomy of the machine will make more sense once we start actually programming it. So this block is connected to other 2 blocks that are called the stacks. We will be talking about this concept in a moment. These arrows mean that they are connected. There's one that is called the working stack, and this doesn't matter too much at the moment, and the return stack. As we are working with, in this low level, so this virtual machine actually uses the same principles that our 64 or 32 bits machines that are organized in terms of, or there's this concept now of thinking about bytes. So just to not just assume that that this is a known concept. No? So the idea of a byte is a unit of information that contains 8 bits. So we have seen in some context now a bit can be either 0 or 1. So a collection of 8 of those that can be either 0 or 1, it's a byte. There are, if you count, it's a fun exercise and try to figure out how many of these possible, how many combinations are here. You will see that there are actually 256 possible values that we can encode using a combination of 80 bits in a byte. Yeah, so this is like a small parenthesis. So these stacks, or these blocks, we will talk in a moment, what are they, can hold each of them 256 of each of bytes. Sorry. Again, this might seem like a little bit so don't feel overwhelmed. If it is feeling overwhelming, it will make more sense in a moment. Also, this machine, so that looks like a little Lego or something, is connected to a much bigger, way more bigger block. So we can say it has a lot of very, very big. Let me move a little bit my whiteboard. Yeah. So this is what we call the program memory. So this one has to do more when we are working with software in general, or thinking about the RAM, the random access memory, or this, or memory in general, when we are looking at these specs. The program memory, in this case, will have depending, it may seem like a little, like very little, but also we are gonna see that actually it could be enough for a lot of stuff. It will have a total of 65,536 bytes. That in some context could be seen as 64 kilobytes. And from this memory, there's a small block that is also 256 bytes that is called the 0 page. I will just put it here. We are not going to use it today, but there's that. So there's the program memory. The program memory will be able to hold either the... Well, it will hold the program, yeah, so that's why it's a program memory, but it will be also able to hold data or data. So either data that we put beforehand, so for example, information about the graphics that we are showing, the sounds that we are playing, or it can also contain like runtime data, no? So variables if you have program already or stuff like that. All of those ideas or concepts will be living in this program memory that, yeah, from my perspective or from the Uxn perspective, is very big. No? So this is 256 blocks of 256 bytes. So when we are programming, we are going to be programming here. We're going to put our program in this memory. And lastly, there's another component. Let me make it a little bit bigger. It's also 256 bytes. But it is divided in 16. Okay, light is coming. Thank you. This block of 256 bytes divided in 16 parts is what will be called like the devices. Port. So all of this is Uxn, the Uxn core, Uxn core, however you want to spell it, or Uxn. This idea of this control unit that interacts, that can follow or can perform 32 different instructions, and that can interact with 4 different blocks of bytes or blocks of memory. So there are 4 different types of memory here. We are going to be seeing what does that imply, but yeah, so we can think that each of them, so this one has 256 parts that are bytes, where each of them has 8 bits. So this is all of this is, again, the Uxn core. So there's no separate registers, just a stack. Yeah, exactly. So we're gonna, for those like know more about these ideas, no? This is what is called a stack machine. No? We're gonna be using stacks, and there are no like registers per se, but we're gonna have this possibility of having memory for storing like values for longer, no? than. So what makes Varvara is this computer that is based on this core, and what makes like Varvara is the I forgot the word, but it's the idea of having like, Varvara defines what should be connected to each of these devices' ports. So for example, there's like this, but this is gonna be like the system device. Then we're gonna have the console device. You can see it, but okay, here's the console. There's the screen. So actually, this is actually what we're gonna be using today. No? So there's a screen connected. So the way of Uxn to interact with the screen via Uxn is through the device port. What else? So there are some audio devices, for example. 3, 4, 5, 6, 7, 8. There's a controller, no, or the keyboard. And for example, there's the mouse also. Well, yeah, so that's kind of a mouse. Yeah, so okay, so this general idea of what's the machine like, no? What does it look like? And again, this is important, and we can take like a little. I mean, I will erase it in a moment, but it's important to keep this in mind. Also, you can screenshot. I will be making a pause here. You can, if you want to screenshot the Varvara computer architecture. Now we're gonna see how does it actually map to programming. How do we actually tell it what we want to do? Okay, yeah. So I'm gonna. So I guess you already took the screenshot. Let me move back to the outline. Okay, so there are questions about Fort. We'll be talking about Fort in a moment. Okay, I'm gonna make a little pause to check the chat. Okay, are there like other questions about what we just saw? The computer architecture. Let me take drink a little bit of water. Okay, so let's go back to the outline. So that was part 1. Now let's go to actually, to start knowing how to use this machine. Tal basics. Sorry, I was not showing this. So the outline. So we covered this. Now let's go to basics. Tal basics. Okay, here comes the fun part. Well, this is fun. The previous thing is also fun for me. I don't know, but I understand that it could seem like a little bit like abstract or like what is going on here. What's up with all these numbers? So we're going to be discussing now this idea of how to use the stacks. Okay, that's great. I mean, honey. We're going to be talking a little bit about hexadecimal numbers. We mentioned already something about bytes, but we're going to be mention them a little bit further. And also there's this idea of the outputs and inputs in terms of the programming language. So just before I erase this possibly beautiful depiction of the Varvara computer architecture, I want to emphasize the idea that these numbers, I mean, for some people could be seen as very obvious. No? Some people would say, okay, these are powers of 2. For some other people, they would look like complete random numbers. And some other people would know that, okay, maybe it's 256 bytes. We were talking before about how many values can be represented using 1 byte. So we can say that 256 is the amount of addresses or the amount of values that can be represented using 1 byte. And in the case of the program memory, this number that we said already is 256 times 256. So this is the amount of bytes or the amount of values that you can represent using 2 bytes or 16 bits. So let's keep that in mind. Okay, yeah, so let's delete this. I hope I can delete it, or otherwise I can. Yeah, it's going. Well, erase it, not delete it. Okay, so we mentioned there were over here some stacks, and in the chat also, no, there's there was also mention of is this stack, is this register, or what's up with that? So let's introduce our first tal instruction. We're gonna start using numbers. So for example, our let me use this other color. Black is okay. So this is a first tal instruction. This is decoded into 2 different bytes, but yeah, so I'm not gonna enter into detail about this. But this idea, so this is a valid tal. What we can read this instruction, or I will read it as a Uxn performer. Whenever I read this, I will think, okay, this is telling me to push into this stack of numbers. And actually the number of stack has to do with how it actually works, and we're gonna see it in a moment. Push this number, 0, 1, into the stack. So let's put the stack over here. So there's this floor. So me as Uxn, I read this, and then, okay, I will push 0, 1 into the stack. Okay, so that's it. That's a first execution of a first, or a first performance of a first program that only pushes one number into the stack. Okay, but this is not very meaningful. Let's try with another program. So there's a space here. I mean, yeah, so this is also in real life non-monospace notation. So there's one command, another instruction. This, when I read it as a Uxn performer, this tells me to push 0, 1 into the stack. And then this other command tells me to push number 0, 2 over a stack. So we can think of the stack, yeah, literally as a stack of numbers. So we are pushing 0, 2 over 1. The idea of a stack, if you're familiar or if you're not with this data structure, it's a structure where we can, or it's called like a last in, first out, or LIFO, no? Or we can think of it that is we can put values, but then we can only take out the last value that was put inside. So here we have another small program. The result here is just a stack with 2 numbers. At the bottom is 0, 1, and the important for us value in this case is 0, 2, that is at the top of the stack. Okay. So we could go on like this, no? For example, I will restart my Uxn performance. I could have another number, and we can start to see, okay, so this is read from left to right. This tells me to push 0, 1, then to push 0, 2, and then to push 0, 3. Okay. Now that we have this concept or this behavior, let's spice it up a little bit. Let's have another instruction introduced now. Add. So as we can infer from its name, add would or means that it's gonna add or perform the operation of addition with 2 numbers. So now let's run this program. 0, 1. So I'm gonna push this into the stack. I'm gonna push number 2 into the stack, and I'm gonna push number 3 into the stack, and then add instruction. Yeah? So all instructions in tal language will be working with values that are in the stack. They're gonna be either or reading value or taking values out of the stack. Some of them might be putting values into the stack after doing something or after performing some operation. But the basic idea here is that all of them will be working with the stack. So we were here. Once we reach the add instruction we can see defined as take the top 2 values from the stack. So take 3, take 2, add them. So the result of 3 plus 2 is 5. So take the two top values from the stack, add them, and then push the result into the stack. So and this idea of having like the operators like at the end, so we can read that this is what is happening here is that this is adding 2 plus 3. This is what is called postfix notation or reverse Polish notation. If someone can put it in the chat, that would be nice. In this case, the operator is at the end, and some older calculators work like this. And the idea here is that as we could follow we'll see how this simplifies many things. But also the idea here is that we are working very closely to this idea of having this stack, or this like memory of numbers that are stacking up on each other. So again, what happened here is that we have now number 1 into the stack, and then we added 2 plus 3. So it's 2, 3, and then add them. And we saw, I can repeat, I love, I love human-powered computers, so I will do it again. I will read this program, 0, 1, push into the stack, push number 2 into the stack, push number 3 into the stack, add, so add is take the first one, then take the second one, add them, and push the result into the stack. If, for example, okay, the problem with here, let's put another add. So we can infer that, for example, if we were following the program and then we reach another like addition operation, another add, what this will do is or maybe you can try telling me the answer. So what will be like the state of the stack after running all this? While I take a sip of water. Okay, so this just like to I didn't have a 6 ready. 1 billion. 6 on the stack. Okay, so actually, let's go again. So this last addition will take what is in the stack already, so that is number 5, number 1. We'll add them, and we'll push the result into the stack. Okay, so there's a question here that if we often push into a variable, or more common to just use the values on the stack. So at least today, and for many like simpler in a way programs, it is enough to just work with the stack. Sometimes, and like for more like complex programs, like the one I was showing you, like I didn't say about this. This is a text editor called Left, made by 100 Rabbits, and it is coded or programmed in Tal. So for something that is more complex like this, it make more sense to have actually like variables and use the other memory like possibilities. But at least, or like part of the charm or the kind of puzzling aspect, but also the fun aspect of this is being able to do like everything just manipulating this stack of numbers. So pushing numbers into the stack, operating on them, then having like this mental map of what are the values inside the stack. If you notice here, when we were doing this process, number 1 was pushed into the stack first, but then we didn't care about it for a while. We pushed 2, we pushed 3. 1 is still there, just like hanging or chilling, or I don't know, waiting. Hope it's chilling. We add this, we had 5, and then we add this, and we had 6. And yeah, and that's a great question that I just saw in the chat. If we add another one, so I'm Actually, it's a great question here because also I'm overflowing my whiteboard. So yeah, also boom. If we're gonna have what's called a stack underflow, no? So the add instruction will try to get two values from the stack. So it will take this one, and then it will not find anything else. So yeah, the program will crash. The idea, or this, yeah. So me as Uxn I will crash because I was not able to. I attempted to pop or to get a value from the stack, and there was not none. So then I cannot do my operation. Yeah, and this crashes. Yeah, so that's a great question, and it came accordingly here. No, I overflowed. I overflowed the whiteboard, but the stack was underflown. Okay. Are there other questions about this? Let me delete that. Erase. Let me give my line for the stack here. So there are other instructions, no? I will like just mention them now. For example, I could just do like 01. There's an instruction called inc that comes from increment. So this instruction will take one value from the stack, add 1 to it, and then push it back into the stack. So when we read this program, for example, we'll have, okay, push number 1 into the stack. Inc. Okay, that means take it from the stack, increment it, so add 1, and then push it back into the stack. So some operations just take, well, we saw, no? Add takes 2 values from the stack, inc takes only 1. We're gonna see other ones that take more. And some instructions don't take values from the stack, but just push them into the stack, and so on. Okay. Let me go back to the outline. So, okay, yeah. So something that maybe you have, well, I was working only with small numbers. All of these numbers, well, actually, when we are working with tal, so this is like another mini complication. When we're working with tal, we're going to be working always notating these numbers as hexadecimal numbers. So that means, and I will not go like a lot into it, but it means that we're working with base 16. So instead of counting from 0 to 9, that comes in decimal, we're going to be counting from 0 to F. So it's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, F. Those are the 16 digits of hexadecimal system. So I will go back to that in a moment or later, but just to keep in mind that these numbers are going to be are going to be written in hexadecimal form. Somewhere in the notes, let me go back to my notes here. Okay, yeah, so there's like these hexadecimal numbers, like page that has like a representation of binary, hexadecimal, and decimal. I will show also in a moment something else that will help us with this. And in the references, there's a decimal to hexadecimal converter. No? So we can say, okay, 256, how much is it in hexadecimal? Okay, it's 100. Okay. Just another like a small, 2 hours. In theory. So let's move a little bit, well, not faster, there's no hurry. I just want to mention another stuff. No? We can either we have been working at this point only with bytes, but tal has one mode that has to do with working with 2 bytes at a time, or what is called shorts. So for example, let's just have here something to demonstrate that. So in order to write 1 byte, we need 2 digits. If we have 2 bytes, we need a total of 4 digits. So that will only allow us to either write 2 digits or 4 digits. So we can kind of see what, well, we could infer what this would do, but actually let's read it. So this like introduction of this literal number into the stack will work as follows. First, we'll push number 0, and then we'll push number 1. Then reading this, we'll push another number 0, and then we'll push a number 2. So this is like a faster way of putting values into the stack. So we are putting 2 bytes at a time, or what we are calling this a short. But keep in mind or look that in the stack they are organized or ordered as bytes. So even though they were like together, this value was composed of these 4 digits. When it's in the stack, we can think of it as it being actually divided into these different bytes. So just to like, if we have here, for example, an add instruction, this add instruction, as we know already, will only take 2 values from the stack, the top 2 values, 2 and 0, add them together, and push the result. Now, fortunately, or I don't know, for some context, it will be all of the instructions will have the possibility of operating, instead of in bytes, operating on shorts or in 2 bytes. And in order to indicate that we are going to be working in that way, we're going to append 2 as a suffix. So it's like, it may seem confusing here. So it's not like I add 2 numbers, it already is adding 2 numbers. Add 2 means that this is the short mode, and the 2 comes from it being 2 bytes. So add 2, let's see what it would do. It will keep the same like template. It will take 2 numbers from the stack, add them together, and push them. But now what will happen is, okay, let's take the first 2 values from the stack, like assemble them as a number, then take the next 2 values from the stack and assemble them as a number. I will answer you in a moment, Thomas. We'll add them as if they were numbers composed of 2 bytes as shorts. So this is a whole number. So the result will be 0 plus 1, 3, and then 0 plus 0, 0. And then we'll push back into the stack first the most significant byte, and then the least significant byte. Those are like the technical names. So the byte at the left or the byte at the right. Okay, yeah, so this is a great question. Like in other languages, we can actually just write 1. In this case, I mean, maybe this was not the best example to use just 0001, because this operation, as we saw already, I mean, we have here the result. The result is 3, but also there's this 0. That in some context will be important. But also, as in 1 byte, as Andy is saying, we can only have values that come from 00 to FF. That means from 0 to 255. If we want to represent like bigger values, so from 00 to 65,535, we need more space. Yeah, so maybe this was not the best example, but for example, if we wanted to, instead of adding 1 plus 2, I wanted to add 0101, that in decimal is 257. So how much is 257? And again, we only, due to how it is like programmed, the assembler, the program that translates the TAL language into the machine code instructions, we need to actually write either 2 or 4 digits, hexadecimal digits. Yeah, so it's a way of writing numbers that leaves room for larger values, as Raskus is saying. Yeah. And also, yeah. Okay. There are 32 instructions, but each of them has a byte mode and a short mode. Yes, no? And actually there are other 2 modes, the return mode and the keep mode. Those get a little bit more complicated, at least for what we're doing today. But yeah, so keep in mind, so that's important. No? There are 32 instructions, but we can have 3 different modes, and they can be either on or off, each of them. So in total, there's 256 possible instructions. Okay, the last thing about this section has to do with thinking about outputs and inputs. So far we have been only working with the stack, but there's interesting computing or computer science that has to do with no inputs and no outputs, just manipulating data. But today, and due to the context, or due to the context of Babycastles, and also the context of Uxn, we're interested in outputs, in this case, visual outputs. So going back to the CAM, there's another we're going to be working with a couple of more instructions that are for devices outputs or devices inputs. So for example, and we will see in a moment actually with the code. We are going to be starting to write code not in a whiteboard, but in a keyboard and electronic computer. So for example, we can have this program, and then this. So that's Deo. Well, I pronounce it Deo. No, I don't know if it's Deo or whatever. No, it's device out. So this part we know already. No? We're reading this. This will push FF, then this will push FF, and then this will push an 8. I will put it in another color for some reason. But it's also a number. No, it's just a number. No? I'm just coloring it differently for. It's syntax. It's kind of syntax highlighting. This instruction will take 3 values from the stack. It will take first, like the value of the stack, the top of the stack, and we'll take this. We'll use this value as an address of a device. And into this address of a device, so we can remember the blocks that I had here drew before. There were 16 blocks of 16 bytes each. So this number will point or will address one of these blocks. And then this instruction will send into that port or into that device this number. So we'll take first the address, then it will take 2 other values that will make... sorry. I'm making a mistake here. Because it's in the short mode, it will take 2 values from the stack and send them into this address. We will see what will happen in a moment. So again, this reiterates the idea of all instructions work with the stack. We will see in a moment what this does. Like the counterpart instruction for this is called device inputs, where we will be, for example, So we know already this. We'll push 96 into the stack. This instruction will take the value from the stack, will read the device that has this address, and will push into the stack the result or the value that is there. So for example, it will push 0. At the moment, I know this is very abstract, but I wanted to just to introduce this idea. Deo or Dio will take values from the stack, but one of them will mean that it is an address of a device, and then it will take some values to send into that device. So it's an output. Whereas they will take a value from the stack that will use as an address from where to read. Okay, again, this might seem a little bit abstract. Let's actually see it in action. Go to the outline. So yeah, so let's actually go into drawing into the screen. But before, are there other questions? Oh. Let me drink a little bit. Okay, so we are almost an hour already. Probably, I'm glad you're liking the pace. Yeah, so this first part is the most important, I think, no? Because this is it combines the main two paradigms in Uxn programming. On one hand, the idea of having, let me go back to the camera, having instructions that actually are converted into single bytes that are stored into the program memory. So that is what makes it an assembly language. Each instruction maps to a specific opcode, it's called, or a specific combination of bits into a byte that whenever Uxn reads them, it knows what to do. So all of these instructions are these single blocks or single operations that single instructions of the virtual machine. And so that's one of the complications or the fun parts about using Uxn that has to do with thinking in these very low level operations, no? Just adding two numbers or just incrementing them, no? Or we saw here, just take an input into the stack, no? Or take one input into the stack or send something into the stack. The other complication is the reverse Polish notation. So can I explain the short? Yeah, so let's actually reperform it. So the other complication is this idea of as we're working with the stack, the most optimal way of working with it is having the operators at the end. So we are putting our operands our operands are put inside the stack first, and then we put the operators. Sorry. So let's perform this. So we have this other program. Let's make something. So again, the idea, or also something that I like, and I'm trying to demonstrate it here. We can code in Tal just in paper, no? Or we don't need. In theory, it uses a simple enough mental model that actually we can do it by hand without having to worry about, I don't know, garbage collection, or I don't know, whatever higher level languages have. Here we can actually just follow it and do it, no? The same way the machine will actually do it. So this will push 0, 0 and 0, 1. Then this will push 0, 1. Oh, I don't have 0, 1. And 0, 2. So it's always pushing bytes. And then add. So this will take two values, but in the form of shorts. So we can, I like the idea of actually thinking of it that it's reassembling the numbers. So it's taking the first two values and reassembling them as a longer value. No? So it's not a byte, but we're going to be taking this number as composed of 2 bytes, 16 bits. Then it will take the next two numbers from the stack reassemble them as one number of 16 bits each. We'll add them. So 2 plus 1 is 3. 1 plus 0 is 1. And then this will push the result back into the stack. First the most significant byte, and then the least significant byte. Okay, we're going to be talking about the idea of the devices, because I see a question about controlling a MIDI device. No? Does it make sense to always use? That's an interesting question, Justina. So they are asking if it always makes sense to have the short mode. Actually, part of the beauty here is that there are many operations or many things that can be done that don't require more than 256 possible values. So that we can actually work with bytes and do a lot of stuff. So the possible problem of always using the short mode is that we are using more bytes than are needed. So in theory, in principle, we have a very short or very small memory that we will see that actually is not that small once we start working in this way. But as we were doing like this, no? When we have 0001 plus 0002, we are wasting these 2 bytes actually in the program memory. And it's kind of funny that in the Uxn community, there's this, not super competitive, but just this idea, there's this idea of, okay, I'm saving 4 bytes from my program. So, and also that's a source of joy and a source of fun. So yeah, so that's a tip. Okay, so let's go back to the outline. Well, drawing into a screen. Okay, yeah, so now after 1 hour here, we're going to actually start writing code you can also run. Let the computer run, not your personal computer or yourself as a computer. We're going to see this side, in general, what does it do, how does it work, and we're going to start introducing actually the devices that will let us draw into the screen. So let's go to the browser. So this link is in many places. No, maybe someone. So if you can share it over there, Lee or Andy, then learn Uxn site that leads us to this page that you may have seen in the promo. Thank you, Thomasers. So this site, and it's kind of, I like that here in the about, there's it says that this isn't permacomputing. I didn't mention permacomputing now, but this is this idea of thinking about computing for a smaller scale. So this is an implementation by Metascene of Uxn into the browser, so we can actually code Uxntal and see our programs running here in the browser. So it kind of, and in one hand, it kind of defeats the point of because part of the story, if you read the story of Uxn, was about running away from web-based frameworks, and then suddenly it's here back again. But obviously, one of the advantages of working with web-based frameworks is that we can use it without having to worry about platform specifics. So yeah, so let's work with it. Here we have this text editor that has already some TAL code, and there's the screen device showing actually the output of the program, and there's some console showing some output, some debug output. Here you can actually see many programs that have already been made. this is what I made when I was learning about Uxn. So this game of pushing rocks around, thinking about maybe you can actually build a computer with this. So the idea is that you can have code here and then assemble it. Assembling is a process of converting the assembly language into the instructions of the machine code. And again, the idea of this being just an assembly language is that it doesn't require a lot of logic behind the translation. For higher level languages, when you actually compile them or interpret them, you have to do like a lot of juggling around in order to actually get to the machine code. Whereas when working with an assembly language, we are actually working with these mnemonics, the instructions that we have been mentioning already, that have like a one-to-one mapping to an actual instruction, an actual machine code instruction. Sorry, camera. Okay, so going back to the browser. Oh no, well, it's okay. Let me go back to the camera, sorry for the changes. Because before this, I just wanted to come back to my other program. To pretend I'm making some magic. So we said, so this was pushing these two values into the stack. Then we were pushing this other value. And this instruction takes this as an address of the device that we were going to be like outputting something. And what we are going to be outputting is these two values. So actually, let's run this here. I'm going to delete everything. If we just assemble this, nothing to assemble, okay. Something important is that, so it is a little bit of notation. No? So in theory, this is what I was showing, but nothing shows. No? If you have the screenshot that I told you to take, or the notes about the computer architecture, the first part of the program memory, that is called the 0 page, is used for other things that are not programs. No? So there's a little bit of notation that I have to add here in order to let the assembler know that I want this program to exist at the beginning of the actual program memory. And the program memory, the memory where the area of the memory where the Uxn is actually starting reading the instructions is located in address 256 in decimal, or 0100 in hexadecimal. I know there's some efforts on how to pronounce hexadecimal. So for example, let's see. Let's run this, and there's some color red. So what's happening here? And I'm also making some mistakes. DO2, as I said, but it's also gonna be red. Now so this is like a little bit of, not magic, but I just wanted to show, okay, this actually is doing something. 08 corresponds to an address of something. So actually, let's talk about it without keeping the mystery. Let me share the browser. From the notes, I'm going to the Varvara documentation. Okay, so I see there's some differences there. Yeah, so you have to add this part over here that will actually put this program into the first address of starting at the address where Uxn is actually reading the program. It's alive. Woo. yeah, so thanks Andy for the program there. So if we look at the Varvara documentation, we can see here so there's a pipe. Yeah, and also I don't know, I wouldn't know how to say, like depending on the keyboard layout, that pipe will be in different places. You can copy it from Babycastles post. Thanks, Lee. So there's this table that has what I was showing you, just with the arrows, and like in the screenshot you took, you could see like some of these. I told you about the system, console, screen, audio, controller, mouse, devices. No? So this table that may seem a little bit like overwhelming at first, or well, not only at first, contains the description or the definition of what should or what is like what is the meaning of the different devices, the ports of the devices, in the computer. So it has like a little strange notation. So we have each device starts with a number. So there's device 0, 0, 1, 0, 2, 0, 3, 0, and so on. And then this shows like the first 8 bytes and then the second 8 bytes. I will not I will just mention this. We can see here that 0, 8, that is the address that we put here, is actually the address for this. It says red. Okay, so it's kind of strange. Okay, what's going on there? It has some connection. No? We are showing some red. Actually, what we're doing here is these 3 values, red, green, and blue, are what are called the system colors. With this instruction, when we are writing to those, sorry, I'm changing back and forth. When we are changing those, sending values to these ports or these addresses, the asterisk means that they are expecting a short, so 2 bytes. When we are outputting some bytes into them, we are actually setting what are called the system colors. Something important that maybe you have noticed in Uxn programs that you have seen. In Uxn, there are only 4 active colors at a time. So let me go back to the camera. Delete this a little bit, erase this. So we're gonna have color 0, color 1, color 2, and color 3. Each of these colors will be, on one hand we have this limitation that is also a source of joy and creativity. No? We're only be able to just draw with 4 colors at a given time. And also each of these colors will only have I'm doing so 12 bits of resolution. So there's a red channel, and maybe this is familiar to you if you have used like HTML or CSS and so on. But instead of having like 2 numbers for the red, 2 numbers for the green, and 2 numbers for the blue, we're gonna have only one digit. So we have 16 possible values for red, 16 possible values for green, and 16 possible values for blue. So for example, we can, and this may seem a little bit abstract. I will go back to the Uxn. I will open the boot room. And also, for example, this is a file browser that has like this character that is animated and this makes sounds. So this is like also like part of the joy of computing. Uxn can't run like modern browsers and crypto stuff and whatever is new over there, but it can be a very nice source of joy. So I was gonna open Nasu. So there's this. We're going to be using this in a moment. I will send you the link in a moment. But we can see here some sliders that can help us like choose no colors. So for example, in this case, and let me draw something here. Let me zoom in. Yeah, so I'm drawing something here. So this color that it looks like a little bit like a magenta is defined by these three numbers. I can change them. So this is the first value is the value of the red. So it goes, as I was saying, from 0 to F. So there are 16 possible steps in the red channel, then 16 possible steps in the blue channel, and then 16 possible steps in the green, and then in the blue channel. Okay, keep this in mind. I will. Okay, so now the like I don't know, a kind of idiosyncratic way of working with colors here in Varvara. These FFF that we are writing here are interpreted as the values of the red channel in the 4 colors. So let me go back to the so that FFFF will be that FFFF that is sent into address 08 is interpreted in this way. So every one of the 4 colors will have as its red channel value this number F. Okay, so now also something that I want to mention before this gets like too confusing or more confusing. I hope it's not too confusing. So we have this specification here. So normally, even though we could actually work with this and just have numbers. For example, in this case, 08 doesn't tell us a lot about what is actually going on here. So it's not very readable. And the idea of any programming language should be that it should be readable to some extent. So this is not very helpful. What we are going to be using is more like notation or more syntax here to help us use these different devices ports without having to remember or to know the different addresses. So, for example, I will take so we're going to see like how do we actually do green in a more clear way. So this is some kind of notation. Also, by the way, at the end of the workshop notes, there is like the example program. Actually, I will be just copying this because it's a little bit artisanal. And so this first part, we can just focus, for example, here in this system part. Is a way that I will not like stop too much at this moment. It's a way of notating this table so that it's saying, okay, there's a label called system that it's sitting at address 00. And then this is making some sub labels in order to have this, the R for red, corresponds to number 8. So in general, whenever you see, you will see many programs that start with this. That is like the definition of the labels for the devices. So that we can go, instead of having this 08 that is kind of cryptic, now what is it going on here? We can actually have this notation, dot system R, sorry. And this is another like feature of the assembler. This is read as, okay, it searches. Where is the label called system? Okay, it's here, it's an address 0. But then the sublabel R is 2 bytes plus 6 bytes. So 2 plus 6 is 8. 8 bytes inside. So this, what I want to say is that this is equivalent to the 08 we had before. But now it's like using, so this label, so we can actually know, okay, this is actually setting the system red color. And for example, we can try on other things. This is setting the green color. And yeah, let's put everything in F for the moment. So, okay, let me assemble this. So this is showing magenta because it's setting. So what is shown at first in the screen is the color 0, the first color. So that first color consists of having a red value of F, a green value of 0, and a blue value of F. Yeah, so that's a good way of saying it, Delia Erickson. These 4 digits are like the amount of red for each one of the colors. Starting from left to right, this is color 0, color 1, color 3, color 2, sorry, and color 3. Okay, confused. Yeah, comments are between parentheses. Make sure that you put a space after and before each of the parentheses so it doesn't mess up. Going back to the camera, we can think of this table. So it's like there are 4 colors and there are 3 channels. So what we have, for example, at this moment is this. So first, color 0 is F0F. Color 1 is FFF. Also color 2 and color 3. But then, for some reason here, it has to do with using the bytes efficiently. No? Instead of setting, okay, I want color 0 to be F0F, what we are setting is this row. No? So we are like transposing, no? this matrix. No? If we want to talk in those terms. No? So we are setting, okay, what is the values for all 4 colors in red? What are the values for all colors in green? And what are the values for all colors in blue? So we're like setting the colors like in this direction. But they have like this meaning. Okay, okay, nice experiments going on here. Yeah, so yeah, the question and answer. Yeah, and just for the sake of the recording, the second. Let me go back to the browser. As red is 2 bytes, it will expect 2 bytes. So red occupies value 8, the address 8 and address 9. The next address is A. That will take, so that green will take. No? So green will be A and B, and then blue will be C. Can they be set in the other direction? No. Yeah, and this is, has some reasons. It has to do with the idea of the ability of sending 2 bytes at a time. Otherwise, we will have like this. If we wanted to send the colors like in each of the colors, we will be like losing one of the digits. Okay. Let me check them. Let me go back to the outline. Drawing the screen. Okay, labels. Okay, we talk about a little bit about the screen device. Okay, let's see these two aspects. Yeah, the sound is great. And again, also that this is great about 100 Rabbits, is that they not only made, they made their own tools, no? Then they made Uxn, and then they are porting all their tools into Uxn, so it's like, it's amazing. If we look at the So we were using here the system device. No? Now we're going to jump to the screen device. Actually, I think I have some notes here. Let me jump to the system device, screen device. Okay. So this has like other addresses, no? So it's like there's a vector, we'll talk about it in a moment. There's a width of the screen that we can read, and also we can write, so we can set the size of our screens in some emulators, width and height. We're gonna skip the auto byte. There's an X and Y coordinate in order to draw into the screen. There's an address, and there's what is called a pixel byte and a sprite byte. All of these that are like a reinterpretation of the table that we were looking at can be expressed as this expression in tal. No? That again is this is just setting some labels. No? It is like normally, so it's a convention to use this notation for the labels, but you are free to actually create your own names for the labels, no? or just work as we were working before, no? Just with the numbers of the addresses. But this is like the template that we normally see. So we already have here in our code the screen device. What does the $sign mean? Actually, something fun I didn't mention about this site is that when you like hover over some elements here, you can see like a little bit of explanation of what is going on. So for example, it says, okay, this rune or this character is actually for setting a literal X. No? This is for a label. This is what it's called a path. No? So it's declaring like the size in bytes. No? So it's kind of, we're going to be working in general with numbers in hexadecimal. No? So everything in here will be in hexadecimal. In this case, the $sign or the pesos sign implies that we're letting like some space in between, of space of 2 bytes or space of 2 bytes. Okay. I'm gonna set my first color as something darker, so actually we can see the contrast of what I will be showing. So for example, let's introduce, we'll see what we are going to do, what we are doing today is just moving values from the stack into different devices and seeing what happens. For example, I will put like some number here that we should be able to read already, no? So we are pushing this into the stack, then we are pushing this address into the stack, and then we are sending it. Now let's do something similar. Another number. These are sublabels from the screen device, no? So they're over here. And now, for example, let's try this. So what I want to show here is that all of this is, I'm using some other labels, no? And we can actually read from the website now what do these labels mean. But these are not different from what we have been doing before. No? We're just pushing values into the stack and then sending them into different devices. No? Okay, it's super small here. I don't know if it comes in the stream, but if you try it in your own computer, you will see that in the close to the top left corner, there's a little pixel, a white pixel. Maybe you can confirm in the chat, that would be great. What is happening here is that we are setting first. So the way this screen device works, the screen device is gonna be drawing into the screen using the 4 system colors. The screen device, in order to draw, needs or requires an X and Y coordinate. If you have used other like programming languages like processing or like in general, not like drawing into the screen, normally has an X-axis that goes from left to right, where the leftmost position is 0. And the Y-axis goes from top to bottom, where the topmost position is 0. So here we are saying, okay, set the X coordinate at this value, that we can read it as 10 in hexadecimal or 16 decimal. And then set this other value into the screen. And then this doesn't do anything until we actually draw. So we're going to have 2 different ways of drawing into the screen. The most simple one is just drawing a pixel. And this value, actually, we can try what happens here. Well, I will tell you. We can see the meanings of these values. I mean, in general, in the pixel, the number we're setting here is the number of the color we want to draw with. So you can try drawing with 0, 0. You will not see it because the background is 0. It's color 0. You can draw with color 1, color 2, or with color 3. In my case, I'm very boring here, and all my 3 colors are the same, but I can start like having some more interesting values. I will use like the official color palette from Nasu, the program that I was showing you. Working stack under flow. Ooh, the debugging is gonna get interesting in this context. In general, and actually something that is important, at the moment I'm just showing the screen, but something that I want to like emphasize a lot is that it is very convenient to actually do the process that we were doing by hand, figuring out, so okay, I will point that out. I just took it as obvious, Andy. But actually, that's the thing. We could be reading this. Okay, this is pushing 2 values into the stack. This is pushing another byte into the stack. And then this DO2 should, as we saw already, should like get rid of 3 values from the stack. So after this instruction, the stack is balanced. We put the same number of bytes inside it that we got out. In this case, the last line I put, I just have 1 byte and then another byte. And the DO instruction takes 1 byte as an address, another byte as a value that will be output, and that's it. If we have here DO2, that's a good error to try. So whenever we have this underflow, is that we are at some point, some instruction is trying to use more values than what are available in the stack. And this has to do because this is not balanced. We just pushed 2 bytes in total, and the DO2 waits or expects to have 3 values in the stack. So in screen pixel, are you okay? So this part over here, it's a little bit too long. Let me put a space here. Maybe you're missing some of them, of these other parts of the code. Sorry that it didn't like wrapped around. So in general, this signature or these labels are like we normally like just copy and paste them. No? You're missing pixel. No. So the codes, the codes and the nodes were there. So you're missing. You mean you're missing the pixel in the screen or pixel in the label? Okay, yeah, just like to show you a little bit. A little bit of like more fun here. No? So in order to draw like 1 pixel at a time, what you could do is just, yeah, so I see there are some people doing pixels already. We can change the coordinate manually, and say, okay, we're gonna go a little bit to the left. If we're not changing the Y, so the value will stay in each of these ports unless we change it, unless we override it, except for the pixel and the sprite values. So, for example, I can just update the X. I can draw another pixel. So I'm setting this color and I'm sending it. So whenever we send something to either pixel or sprite, we're gonna be like actually executing or performing the drawing. I mean, again, in my case, I cannot see a lot, but I could just go on like this. No? Doing some pixel art via TAL programming. No? Yeah, so in general, and actually that's a good question. No? So when some of these have a value of 2, so they're shorts, and some have a value of 1. In the table of the devices, we can see that whenever those values are shorts, the name will have an asterisk. So in this case, system vector, red, green, and blue, expect a short or have a size of 2 bytes. Whereas the other values are only 1 byte. Awesome. Okay, yeah, so this is one way, and then we could have like some logic to actually draw more pixels in the screen, but actually let's go to like another fun and exciting and also efficient. Not that efficient is necessarily a value to strive for, but in this case it will be helpful. Instead of drawing pixel by pixel, we can actually draw what are called sprites. We can draw a collection of squares or tiles that are 8 pixels wide and 8 pixels tall. So for that, I will go to, let me see if it's here also. Okay, I will show you with the keyboard, the whiteboard, sorry. Let's erase our colors. More human-powered computing. So if we think of these tiles, and then again, right? 1, 2, 3, 4, 5, 6, 7, 8. Sorry, because my grid is not super precise. 1, 2, 3, 4. Well, if you have like grid paper, it will be better. Yeah, exactly. No? It's not trivial to draw a line. But the idea is that so we can draw, instead of 1 pixel at a time, we can draw blocks of pixels that are 8 times 8. And actually, many years ago, I saw a video about how, like, I don't know, like sprites, or I don't know, like Pac-Man, no? The character was drawn, and it was a process like this. No? So, for example, we can say, okay, from this grid of pixels, I want to color. Should I do it easy or difficult? Let's do it the easy one. I want this to be on. So we can think of in this first mode, we can think, okay, this is we're turning on, or we are setting as 1, all of the pixels in this row. So it's 1, 1, 1, 1, 1, 1, 1. That in hexadecimal will be written as FF. That is also true here. In this case, there's 1, 0, 0, 0, 0, 0, 0, 1. In the Uxn suite of programs, there's one called Calc, and this you can get from. Sorry, I'm not. Yeah, I'm showing it. This you can get from the. There's over there somewhere link Uxn source code where we can actually look at the programs that are here. So there are projects, software, for example, Calc. So you could, in principle, like copy all this and paste it into this emulator. No? I will not do it in order to not delete my own code, but I have it running over here. So just like, yeah, this is also like a very nice tool to have. We can see here, okay, so I can put here some turn on or off some of these that represent bits. For example, all of these, 1, 1, 1, 1, 1 is FF, as I was telling you, and in decimal is 255. If I go 1, then 0, 0, 0, 0, 0, 0, 1, this in hexadecimal will be encoded as 8, 1, and in decimal it's this number, 129. In decimal it's just like, well, I was gonna say for the lols. It's not for the lols, but it's like good to know. But the important part is here, no? This pattern, 1 and then 6 zeros and then another 1 is encoded as 81 or 81, sorry. Yeah, so all of this just to say that we can think of this state or this tile that consists of 8 times 8 pixels. We can encode it, each row, as a binary number that in hexadecimal is written as this. No? So we have this data, FF, then many 88 ones, and then FF. There's also a very nice program by 100 Rabbits called Nasu. That is what I was showing you before. It's at the top. There's a zoom tool over here, and I can do the same. Now I can draw. There's over there somewhere over there the link to this tool, so we can see I drew this square. Here it looks way nicer. No? The grid is okay, and I can see here in purple the same numbers that I was telling you. No? FF, then 81, 81, 81, 81. So this is the encoding of this sprite. For a moment, I will only use this one color, but we could also use like more colors. No? Actually, let's do it. Whenever, if I start to use more than one color, I will see that the other part here starts to get some numbers as well. Okay, so now what does this mean? So this tool, Nasu, is helping us encode a sprite into like into hexadecimal, so we can actually draw with it. So actually, let's go and jump through that or towards that. I will go back to the browser. And there's an instruction called break that allows us to stop the flow of the program, and also allows us to like input some data into our program. So I can say something like this. So I don't know, my brush. I will put here the numbers that I was telling you in groups of 4. So as you can see here, these are only like the hexadecimal digits. I'm not using the literal X run. So this is not being pushed into the stack. This is like just like hanging there in the memory. This data, this set of numbers is there in the memory. In order to actually draw with them, to draw this information that encodes a tile, a sprite, into the screen, what we will do is change a little bit our program. No? Instead of setting up or setting a pixel, first we need to set or send to the screen device the address of the tile data. So again, this is more notation here. This semicolon is for pushing into the stack the address that corresponds to this label. We are sending into this port of the screen device the address. We're sending it. And then we can draw it. Going back into Nasu, we can see here this grid of different different ways the sprite looks depending on like using different types of colors. So for example, I want it to look like this, 80. So I will use this number. And I mean, I know that some of these numbers are like, okay, what is going on with these numbers? The Varvara reference also has this. I mean, it's kind of cryptic, but it's less cryptic than before. And also, I saw that some of you like shared there's a tutorial now that I wrote that has a little bit more in-depth explanation of this byte. But for example, I will say, okay, I will put a number, just a random number, almost random, and send it as sprite. It's only 1 byte, so I'm only sending deo. Okay, so there's a square. I don't know if because this is like super downscale, I don't have a big screen that I'm not looking at the line at the bottom. But like the easiest way to try is, okay, maybe we can have another brush that is all, everything in F would mean that it's all filled. I have one. Okay, so there's one. Thank you. Yeah, so it should be groups of 4. Thanks. What? Okay, so now it's not running. I don't know what I did. I put another. Yeah, so here's I put an extra F. Sorry. Yeah. Woo! So here's our square. I really recommend, I mean, the approach of drawing like by hand and then like encoding that information into the hexadecimal digits, putting them into program memory, and then setting that data as the address or a sprite, and then drawing it can be very like fun, no? And yeah, and joy, source of joy again. Okay, I will leave here the code for a moment. Let me, meanwhile, open again the outline. Are there other questions? So we're gonna attempt to cover like the last part that in principle should be, we will see that it's basically the same, just getting some meaningful values, no, and outputting them to different devices or devices ports. In the case of if you were using NASU and you had, I closed it already, no? But you can look at the tutorial that was linked, and I will link it, talk about it in a moment also. There's an explanation of we can have sprites that are just using one color or two colors at a time, or sprites that use four colors at a given time. I want to talk a little bit about this last part, that is like whenever they a little bit more fun comes. No? Yeah, so there's a there's a question, no? If we can make programs that don't require graphics, no? Yes, there's a console device that works more or less in the same way. No? In the online tutorial, actually we start covering the console device, no? That lets us either write bytes into the system out or getting bytes from inside, no? From std in. Okay, yeah, so apparently I'm losing my mind. No, it's okay. Just let me check again the outline so that we can just... Yeah, so probably we will not be able to cover the conditional behavior now, but the tutorial is a great source for that. But we can cover the interactivity now. Or maybe we can cover it. Let's see. Back to the code. Another one of the ports that is super useful and used from the screen device is what is called vector. And this, I want to talk about this because also this is like a concept that will be used or will be very powerful, no, for many other applications. The idea of a device vector is that this will receive an address of a part of a program that we want to run whenever the corresponding like event to the device happens. In the case of the screen, that event is a tick that goes at 60 hertz. So 60 times per second, the screen vector is called. So in other contexts, if you have used like processing or open frameworks and stuff, there's like this like draw loop, no, or drawing loop that is repeating at 60 times per second, and then we can do like some fun stuff there, no? Taking the advantage, because at this moment what we have been running is just like running once and then stops, and that's it, no? The draw loop behavior and interactivity loop behavior allows us to be able to update our programs at this rate. So the way we're going to be using it, I will be open. So I closed this, that we can say that this was like the on reset routine. Actually, this is called from the system vector. We don't have to set it. It is set by default. This add is a way of setting labels. No? We can have another one on frame. And the way this would work is like we are going to say, okay, this is part of the setup. We are going to say, use this address whatever is inside on frame, we want to execute or perform 60 times per second. For example, we could have the drawing happening here. This will look the same or not. What's happening? Sorry, it's screen vector. And just as a little demo, I mentioned before, no, there's a counterpart of the deo instruction that is day. So we can just have something like, okay, we can read, so this address, read it into the stack, maybe increment it, and then put it. So take the 2 bytes that correspond to screen X, increment, add 1 to those 2 bytes, and then send back as an X coordinate, and then draw. So this will just, on one hand, this helps us to see a little bit more complex operation, but it has to do with using the stack. We can read it by hand as we were doing it before. This pushes something, this consumes this item and pushes something else, increments it, and then we send it. When we have something like this, we have animation. Each frame at 60 times per second, the screen X coordinate is being updated, it's being incremented. And what is happening actually in the example code that I wanted to cover now to show you is, instead of having, I will comment this so that it's available there. We can also actually use, for example, the mouse device. The mouse device has a vector, yes, but it has an X and a Y coordinate. So we can do something. Okay, so each frame at 60 times per second, maybe we can read what's the X coordinate from the mouse into the stack, and then we can send it out as an X coordinate in the screen. So again, this is some kind of assignment, no? But in other languages we would say something like, okay, X coordinate equals mouse X. In this case, we have to do this procedure of setting the address, then doing the operation, no? Getting the value. Then setting the address of where we want to send it, and send the value. So now at 60 times per second, we have this process of getting the X and Y coordinates from the mouse, setting them as X and Y coordinates for the screen device, and calling the screen sprite port in order to actually draw it. So that's I mean, I just did it as very casually, but no, yeah. So now we went from drawing from a whiteboard and speaking or talking about the Varvara machine and Uxn in general, to actually code or have this set of instructions that actually draw, no, allows us to draw in the screen with our mouse, for example. Yeah, so I will, as I was saying, no, I will not go for a moment to the conditional part. Actually, the notes have the example, so it's just an extra line, but it will require more time to actually talk about it. I don't know if there are like other like general questions about what we just did. Okay, the onReset label is actually not used. We put it there like just for like clarity, or just like as a convention. Actually, at some point in the output, I don't know if in the output here, but in the output of the like the official assemblers, they say that this label is not used. But helps us visualize the idea of normally what we have like as these subroutines will start with some label and will end with some break instruction. Okay, let me go back to the outline. Drawing, so we did draw. The conditional will be like for later. Okay, so some questions, but I will leave here these notes. My personal relationship. Well, I'm part of the Merville community, and where there are 100 rabbits are there. And I mean, I loved the project, and then like I was getting too into it. I have programmed a couple of programs. I was showing you the arena and other stuff, and I have enjoyed a lot of experience of programming with Tal, because this idea of this is a machine that can fit inside my head, and actually I can code or program, for example, in paper, in my whiteboard, I can be running and be thinking about manipulating the stack. So it's like this puzzle activity and fun and engaging and enjoyable activity. So I mean, I got into Uxn because of Megville, but then that's why I was so into it that I decided to write the tutorial that I was linked over there. I will talk about the tutorial in a moment. And yeah, and now thanks to Babycastles, I can also be able to talk to you all about it. Can programs import libraries? There's like a rune in order to import other files. You can see when we were talking about the Uxn repository, there are some programs over here that you will see, or actually in the programs that 100 Rabbits make, for example, Nasu or Left, some of them you will see in their code how they are importing other files. The concept of library, I mean, at this point, it's more about the joy of solving the problem, but there are some kind of libraries in process for, I don't know, manipulating 32 bits or stuff like that. How do you connect Uxn to the internet? So I was gonna mention. So in the workshop notes, there's like this that says that there are links and resources for the workshop and more. So this Uxn tutorial is what I was telling you about. So it's actually like a slower pace. In this case, we have like this slot of time that in a way is like some kind of introduction to the concepts. The whiteboard part was like the most important, maybe, like figuring or realizing how this stack handling works. But then, for example, this tutorial goes slower. Actually, we covered today it's a little bit in day 1, day 2, I think in day 4 and 5. I recommend you to, on one hand, to engage with the community, either in the Fediverse, or I don't know where you are, but probably there are some people around there that know how to code, or in Uxn, there's an IRC channel. The tutorial, again, goes slower, no? In theory, 1 day at a time, no? The idea is that you can spend like 1 week here, no? Maybe some of these days require maybe 1 hour or something, no? Or a couple of hours maybe. But then it details better the process, no? Or the reasoning, or also the notation, no? Because here we had to introduce a lot of symbols that are not super obvious. Okay, yeah, I'm glad that the tutorial is less frightening now. Yeah, and the device part, I mean, also the idea is that most of the 100 rabbits philosophy, and also like here, no? Like the idea is that the code, if it is possible or it makes sense to have it self-contained, no? In one file, it would be better. Yeah, so the boilerplate of the devices, that was the question, no? It could be tedious to be like writing this. So in general, it's like just copy and paste it, no? There's actually like an empty file or empty or template or something like that, no? Blank that has like all the devices that you can like choose from here and just copy and paste it. Yeah, so going back to the outro. So there, and also from there you can see like other resources. There are like many programs, many like, I don't know, like plugins for your favorite text editor. Well, eventually, this video also will be available over there. And I invite you all to like support Babycastles, no? And also 100 Rabbits, and also Computanzas. You can see, you can also get those links from the notes. And I think I have a final slide here. Woo! Yeah, so thank you. Thank you all for being here. See you around. You can find me in the, also there's in the website that was shared in the notes. You can see like some ways of contact. Thanks. Woo! Celebrate. Yeah, so supporting, by getting into this workshop, you are supporting Computanzas. Yes. Thank you. Woo. Okay, yeah, so see you around in the internet. And also share with us all whatever you create with Uxn. We'll be very excited about what you create with this. Bye. Yeah, so as I was telling Lee before, I don't know how to close this. Lee told me how to close. Yeah, so thank you all. Woo. Let's go back to the camera. And then do some erasing. Bye-bye.